Hello all, welcome to the new lecture of integral equations. In this lecture, we will discuss about the section 3.10, the Neumann series. Here we mainly discuss about some iterated kernels, or it is called a resolvent kernel or reciprocal kernel, and the method of calculating the solution of integral equations of second kind using the resolvent kernel or reciprocal kernel. So in this method, first in the method of iterative methods or successive approximation methods, we have defined one operator, integral operator kappa, as kappa of f of x is equal to integral a to b k of x theta f theta d theta, and using this integral operator, we have formulated the solution as y of x is equal to fx plus summation lambda raised to n kappa raised to n of f of x. Like this, solution will be in this form. So we are again redefining this, or we are defining kappa here also, and find kappa square fx, kappa cube of fx in some another manner, or using iterative kernels. So we try to write the iterative kernels. So kappa of f of x is by definition integral a to b k of x theta f theta d theta. Then kappa square of x means kappa of f of x. So this will be integral a to b k of x theta kappa of f of theta d theta will be there. So again we need to write the integral, since kappa itself contains an integral. We write instead of theta, we write the dummy variable as theta 1. So the integral becomes integral a to b k of x theta 1 kappa of f of theta 1 d theta 1. So instead of theta we have taken theta 1. Now we have to find kappa of f of theta 1. What is kappa of f of theta 1? By equation number 1, kappa of f of theta 1 will be integral a to b. Instead of x, here it is theta 1. So we have k of theta 1 theta f of theta d theta. That will be kappa of f of theta 1. Now again rearranging the order of integration, we will take the k functions, the kernel functions in together. Then we have integral a to b. Then first we find the integral with respect to d theta 1. So integral a to b k of, we know in with respect to d theta 1 f of theta is uh, constant, can be considered as a constant. So whenever we first write the integral d theta 1, we have integral a to b k of x theta 1 k of theta 1 theta d theta 1 into f of theta d theta. So integral a to b, again integral a to b k of x theta 1 k of theta 1 theta d theta 1 into f of theta d theta. Take it as equation number 2. Now if we define the iterated kernel k2 of x theta by this relation, or if we name the integral that comes under the integral sign, or which comes under the bracket as the second iterated kernel k2 of x theta. By that means k2 of x theta is equal to integral a to b k of x theta 1 into k of theta 1 theta d theta 1. This is the second iterated kernel k2. Then equation number 2 becomes kappa square fx is equal to integral a to b k2 of x theta f theta d theta. Let this be equation number 3. Also we write k1 of x theta as k of x theta itself, the kernel itself. Then first iterated kernel is the k1 is k of x theta, and we define like this k2 then k3. What will be k3? K3 of x theta will be integral a to b. We can see that k1 of x theta is k of x theta, k2 of x theta is integral a to b k of x theta 1, then k1 of theta 1 theta. Actually it was k of theta 1 theta, and we have k of x theta is k1. So k1 theta 1 theta d theta. Then similarly we can define k3 as integral a to b k of x theta 1, then k2 of theta 1 theta d theta 1. So we can repeat this process, and we will get the nth iterated kernel kn of x theta as by the formula kn of x theta is equal to integral a to b. Hence the nth iterated kernel is defined by the formula kn of x theta is equal to integral a to b k of x theta 1 k n minus 1 theta 1 theta d theta 1 for n equal to 2, 3, 4, etc. Now substituting all this in corresponding equation, we have kappa n of x, kappa n of fx is equal to integral a to b kn of x theta f theta d theta. Similarly, in the case of equation number 3, kappa n of f of x is equal to integral a to b kn of x theta f theta d theta, where kn of x theta is the nth iterated kernel. Similarly, we can formulate kp plus q of x theta as integral a to b kp of x theta 1 kq of theta 1 theta d theta 1 for any positive integers p and q. Now, if k of x theta is bounded in open interval a b in such a way that mod of k of x theta is less than or equal to m, then it follows that mod of kn of x theta is less than or equal to m raised to n into b minus a raised to n minus 1. This is because when we calculate k1 of x theta, we have a modulus of k1 of x theta is same as mod of k of x theta, which is less than or equal to m, and mod of k2 of x theta is by definition mod of integral a to b k of x theta 1 k1 of theta 1 theta d theta, which is less than or equal to integral a to b mod of k of x theta 1, and mod of k1 of theta 1 theta will be less than or equal to m into m, that is m square into integral d theta 1 will be b minus a. So this will be mod of k2 of x theta will be less than or equal to m square into b minus a. Similarly, k3 mod of k3 of x theta is less than or equal to m cube into b minus a raised to 2. So in general, we can have mod of kn of x theta is less than or equal to m raised to n into b minus a raised to n minus 1 for values of x and theta in open interval ab. Now, for the equation of the form equation number 8, integral equation y of x equal to fx plus lambda integral a to b k of x theta y theta d theta. By the iterative methods, we have formed the solution in the form y of x equal to fx plus summation n equal to 1 to infinity lambda raised to n kappa n of f of x, where kappa n of f of x we have formulated as 5 integral a to b kn of x theta f theta d theta. Now substituting that value here, we have the solution is in the form summation n equal fx plus summation n equal to 1 to infinity lambda raised to n integral a to b kn of x theta f theta d theta. Now interchanging the summation and the integral, we have f of x plus integral a to b summation n equal to 1 to infinity lambda raised to n kn of x theta, this in bracket, into f of theta d theta. Or when we replace n by n plus 1 and taking 1 lambda outside the integral, we have f of x y is equal to f of x plus lambda integral a to b summation n equal to 0 to infinity lambda raised to n Kn of Kn plus 1 of x zeta, f zeta, d zeta, represented by equation number 9, and this will be the general form of the equation in terms of the iterated kernels. This will be the solution in terms of iterated kernels. So we now have formulated the solution as in terms of iterated kernels, and there is a series under the integral sign. There is summation n equal to 0 to infinity lambda raised to n kn plus 1 of x zeta. That means the series in lambda and the iterated kernels for sufficiently small values of mod lambda. The series inside this integral equation, inside the integral of the equation number 9 is known as the lambda, is abbreviated or denoted as lambda gamma of x zeta gamma lambda, gamma of x zeta lambda, that is summation n equal to 0 to infinity lambda raised to n kn plus 1 of x zeta, and this series is known as the resolvent kernel or the reciprocal kernel. So reciprocal kernel is gamma of x zeta lambda, and this is expanded as k of x zeta. First when n equal to 0 it will be k1 of x zeta, that is k of x zeta, then lambda k2 plus lambda square k3 plus lambda cube k4 plus etc. So this will be the series. So equation 9 will be in the form by writing this as gamma of x zeta lambda. Then the solution will be in the form yx is equal to f of x plus lambda integral a to b gamma of x zeta lambda f of zeta d zeta. Now the function gamma of x zeta lambda is known as the reciprocal or resolvent kernel associated with the kernel k of x zeta in the interval open interval ab, and the series in 10 or the equation 9 or the series 9 is known as the Neumann series. And by equation number 7 we can have the k of x zeta, or we have the iterated kernels kn of x zeta is modular, it is bounded, and it is bounded by m raised to n into b minus a raised to n minus 1. Each iterated kernel is um, um, bounded, and hence by the uniform convergence or by the convergence test for a series of functions, we have this series converges uniformly and absolutely when mod lambda is less than 1 by m into b minus a. Or more precisely, we can say that the series converges, the Neumann series converges, or when mod lambda is less than mod lambda 1, where lambda 1 is the smallest characteristic number. So this about the Neumann series, resolvent kernel and the corresponding Neumann series. So in the iterated kernel itself, we have formulated the integral operator to make the calculations simple. And in terms of the integral operator kappa, we have formulated a solution for the equation, integral equation. And we now turned this integral operator. Using the integral operator kappa, we defined the iterated kernels k1, k2, etc., kn, and using these kernels, we have formulated a series known as resolvent kernel or reciprocal kernel, and using that, we have obtained the solution in terms of the Neumann series, and which converges absolutely and uniformly when mod lambda is less than 1 by m into b minus a, or more precisely when it is less than mod lambda is less than mod lambda 1, which is the smallest characteristic number. So this is about the theory of Neumann series and the iterated kernels. Now we move to the problems that we will discuss later.